Okay, so as promised, we're now going to consider our third organometallic reagent. I'm going to say that slowly because I get the syllables mixed up. There's so many of them. But our third organometallic reagent, and it actually has two alkyl groups on it, but only one of them is going to be useful to us. That's why I put this in red over here. So you're going to have to get your eyes used to that. So the way we make that is we take an alkyl halide, as we've said before, and we make an organolithium compound. You've seen this. This we did in the last conversation. But then after that, we take another Cu, let's say CuBr, okay, for example, as a halide. But we take a half equivalent of that, and we make this. All right. So this is our Gilman reagent, and I will oftentimes write this as C is R2 CuLi. If I'm trying to keep things straight in my head, I might do it like that, right? It's the same thing. So you might ask, why are we doing this if we're going through an organolithium step? Well, first thing is so that we can get points on quizzes and exams, right? You're asked to recognize this reaction. In a couple slides, I'll show you how this is a special reaction, and we can do some things with it that were otherwise inaccessible. But before we do that, let me help you appreciate that Gilman reagents can be either alkyl, you see a primary carbon here, or vinyl. That's a vinyl right there. When you have a bond on a double bond, that's vinyl. Or aryl, okay? An aryl is when you've got an arene, right? So this is an aryl halide, right? Arene, aryl halide. This whole thing is an aryl halide. This is an arene, and this whole thing is an aryl halide. Okay, and so here's what we make it, right? Just you saw this in the previous in the previous slide. We first of all make the organolithium reagent, and then we chase it with this stuff in our second step, and we make the Gilman reagent. And this is what you make. Okay, so can you see this is my R group, and here's my R group, right? So this is going to be a matter, I think, of slowing down, making really good notes, and saying, all right, I get that I've got an alkyl group on there, and I've got two of them, so it looks kind of scary, but if you're okay with slowing down and stopping and drawing everything out, you'll be fine. So same thing here, right? You see that? And here's my vinyl group, okay? All right, so Gilmans are selective, and that is that they can, you can add things. We're not going to be even using these reactions. I'm gonna leave this in the video, but we're not going to be doing those reactions for now. We'll be doing those reactions later. Let me skip that. So Gilman reagents can undergo coupling. This is cool, with an alkyl halide, and this is called a Corey-Posner-Whitesides-House reaction. Corey-Posner-Whitesides-House reaction, and that is I can take one of these R groups, right, one of these R's, and I can couple it with this other R. So they could be different things, right? So if I have, for example, suppose I've got that and that, and I want to make, how many carbons is that? 1, 2, 3, 4? 1, 2, 3, 4? Well, I can't do that in one step, but I can do it in two steps, right? I can first of all make this into my that, and I can make that. Well, that is that, right? And then I can put them together, and I can make myself a carbon-carbon bond. The magic here is we can make a carbon-carbon bond. These reactions are done at low temperature and with diethyl ether or THF as a solvent for reasons just like we described before with the magnesium and lithium reagents. Now here's the cool thing. A cool thing about this is, I guess this is pretty much what I showed you in the previous slide. But a cool thing about this is that these are selective. Look at that. If I've got an iodide here, right? We're not going to get into the mechanism for this because I don't understand it, and it's beyond the scope of this course. But this is simply going to replace my iodide with an R, right? And I think the next slide shows something even. It does, yeah. Well, this is cool. This shows something even more dramatic. Can you see how this is the E that's in the E configuration? Well, if I replace my iodide with that R, it's still going to be in the E configuration. Get your eyes used to looking at that. That's amazing. So as I said, the mechanism is not well understood by me or maybe anybody else, and it depends on several things which we're not going to get into. So because the Gilman reagent is somewhat selective, this is compatible with lots of different things. So I've got this sort of weird reagent. Can you see how this is the same thing as R, right? And I can replace my I with that, but it doesn't touch this over here. It doesn't touch it at all. So this is a great reaction because this is not going to do anything over there. It's simply going to replace that iodide. All right. I think I said this before. Coupling allows us to make longer carbon chains by taking two alkyl halides and putting them together. So if I were going to make something like this, suppose you were asked to make, well, like I did in a previous slide, suppose that I would ask you to make a 4-carbon compound from compounds that were 3 carbons or less, right? So what you would do is you might take a 1-carbon compound here, a 3-carbon compound here, right? Where that is that R, and that is that. And you would, and this right, remember how this arrow says this comes from, that's what that arrow means. This comes from this over here, right? And that comes from here. Do you remember how to make that? Okay. Do you remember how to make from an alkyl halide the Gilman reagent? That's just at the beginning of this conversation here. All right. So then we just turn it around. If you're asked to synthesize this stuff, you first of all you retrosynthesize it. In other words, you look at that and say, how do I make a 4-carbon compound? And so you'd say, well, that must come from compounds with fewer carbons in it, right? And this Gilman reagent's got to come from that, okay? And so then we just turn it all around. And I encourage you to draw this out. Replace the R with a real alkyl halide. Replace both of these with real alkyl halides. And let's say that are not equivalent, where R red does not equal R prime blue. And see what you get. You need to go practice this. Your eyes will get used to it. Looking back on it now, I frankly, I forget why I struggled with this in the beginning. I hope the same for you. Hope you get there quickly.